Hello, Algebra 1 students. This is Mr. Kraft coming to you from my living room. I want to talk a little bit about operations with scientific notation. Now, we talked the other day about how scientific notation is just a way to write very large or very small numbers by rephrasing everything in terms of a number. If you remember the number part, we call the mantissa, times a power of 10, which we call a power of 10. So the question arises, what if you want to add or subtract numbers that are in scientific notation? Because the other day we talked about just how you convert them into scientific notation or into standard notation. What about if you want to add or subtract or multiply or divide? What do you do then? Well, we'll start with addition and subtraction because they're actually in some ways harder than multiplication or division. The simplest case is when you have something like this, where you notice on both the exponent parts, the exponent's the same. So in a case like that, you just take your mantissas and add them the way you normally would with decimals, and then you tack on the same power of 10. So 4.2 times 10 to the 6th plus 3.4 times 10 to the 6th, 7.6 times 10 to the 6th. Easy peasy. If that had been subtraction, 4.2 times 10 to the 6th minus 3.4 times 10 to the 6th, you would have 4.2 minus 3.4, and you would do that in the usual fashion, end up with 0.8. You have 0.8 times 10 to the 6th. Well, that illustrates the first situation that sometimes can occur in a case like this. You don't want 0.8. You never want something that's less than 1 or more than 10 for your mantissa. You have to move this to the right to make it 8. But if you move to the right, you are basically multiplying by 10, right? So you have to take this down 1. And just to prove to you that that works, you had 0.8 times 10 to the 6th times 10 to the 6th. You go 1, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that gives you 800,000. If you just had 8 by itself, you moved 5 places to the right, which is what you do here. 1, 2, 3. 1, 2, 3, 4, 5. You get the same answer. So when you have to move this decimal to the right, you take the exponent down 1 to compensate. Okay. So basically, when you're adding or subtracting and the exponent's the same, the only thing you need to watch out for is fixing your mantissa. So to give another example, if I had 7.9 times 10 to the 5th plus 8.3 times 10 to the 5th, well, this is going to cause me the opposite problem. I'm going to go over 10. 1 plus 7 is 8. 8 plus 8 is 16. I'm going to get 16.2 times 10 to the 5th. And this is the opposite of what I just did. Here I have to go back 1, which is equivalent to dividing. So that means this goes up by 1. You never leave it as 16.2 times 10 to the 5th. You have to have it as 1.62 times 10 to the 5th. Okay. What gets really interesting, and you've been in my class long enough to know that if I say interesting, you're going to have to think, oh, gee, what's going to do now? Let's say you have 5 times 10 to the 8th plus 6.1 times 10 to the 9th. Well, now we've got a problem. Our exponents on the exponent part are different. So we cannot just simply add these as is. And basically, what we're going to have to do is find a way around that. So what I'm going to look at is this. This is something you'll see in greater detail when you get to Algebra 2. It's a little sneaky thing that you do by following the rules of algebra. So what I'm going to do, I'm going to forget the mantises for a minute. I'm going to say 10 to the 8th. I'm going to say, gee whiz, if that would have been 10 to the 9th instead of 10 to the 8th, we would have the same exponent, and we could add these and life would be wonderful. So I say, well, if I just multiplied that times 10 to the 1st, that would give me 10 to the 9th. That's what I need. But if I multiply it by 10 to the 1st, I'm changing it. I can't just change something to make it be what I want it to be. It's like if I got $5, I can't just say, well, that's actually $10, and boom, it actually changes. I can't do that. So I can't do that here. What I can do, though, is something really, really sneaky. Now watch this carefully. I know what I'm about to do is going to look confusing, but stay with me. I'm going to say 10 to the 8th times 10 to the 1st times 10 to the negative 1st. You probably say, what in the world is he doing? Well, these two guys, 10 to the 1st means 10. Hopefully you remember that 10 to the negative 1, a negative exponent, means a fraction. So 10 to the 1st times 10 to the negative 1 equals 10 times 1 over 10. Cross cancel equals 1. So these two guys right here are equivalent to 1. 1 times 10 to the 8th doesn't change it. So here's where I want to get really slick. I'm going to say 5 times 10 to the 8th times 10 to the 1st times 10 to the negative 1st. Well, even though I use the symbols for multiplication differently, I use my little X here and I use the dots there. It's the same thing. Recall the commutative property. The commutative property says that when you're multiplying things together, the order does not matter. So just to give you an example up here, this example is not part of the problem. It's just to illustrate. I'm going to change color so you know it's not part of the problem. 3 times 2 times 4 is the same thing as 3 times 4 times 2, or 4 times 3 times 2, and so forth. So, what I'm going to do, I'm going to take this, and using the commutative laws, I'm going to rewrite it. 5 times 10 to the negative 1 times 10 to the 8th times 10 to the 1st. All I did was I took this guy here and moved him over there. That's all I did. I'm allowed to do that. Now I'm going to use the associative property. Associative says that when I'm multiplying a bunch of stuff together, the way I group it is unaffected by where I decide to put parentheses. So I'm going to group these two together. 5 times 10 to the negative 1 times, I'm going to group these two guys together. 10 to the 8th times 10 to the 1st. Well, 5 times 10 to the negative 1 is 0.5. A negative exponent means you back up one place with a decimal. 10 to the 8th times 10 to the 1st is 10 to the 9th. Because remember, your rule is you add exponents. But look what's happened now. I now have the same exponent. Now we're good to go. So now I've got 0.5 times 10 to the ninth, and I just rewrote this with the x symbol. Parentheses means multiplication, that means multiplication too, plus 6.1 times 10 to the ninth. Now, normally, under normal conditions, that's not acceptable. We don't ever want to have a decimal as the mantissa. But this is just temporary. It's going to go away. I'm going to add my two mantissas like I normally would. So I've got 6.1 plus 0.5 is 6.7. Kabam! We've got the right kind of mantissa now. It's just what we want it to be. 6.7 times 10 to the 9. And that, ladies and gentlemen, is our answer. I'm not going to do any more examples of this because I do realize this can be confusing. Follow it through in your textbook. Watch this video closely. Rewatch it if you need to. I want to save any more discussion of this for a live Zoom meeting, which I've been messaging you about constantly for the last couple of days. What I'm looking at right now is Friday, maybe. We'll see. But this is something where I'd rather be able to have you talk to me in real time when I can do these. So what I want to do now is talk about something that is very easy, which is multiplication. Multiplication and division of these guys is about the easiest thing you can possibly do. It's wonderful. So let's say we had 3.2 times 10 to the 5th times 4.1 times 10 to the 12th. And as you may guess, or if you haven't guessed, or if you haven't got it from the textbook yet, I'm telling you, different exponents with multiplication and division are not a problem. Basically, by the commutative property, I'm doing the same thing I did earlier. I'm not going to go into as much detail. By the commutative property, which says I can change the order, and the associative property, which says I can group them differently, since this is something times something times something times something, I just rearranged it. Put the mantissas next to each other, put the exponents next to each other. Exponents are easy. You add them. 5 plus 12 is 17. 10 to the 17th power. These guys I multiply the same way as I would for normal decimal situations, which means I ignore the decimals. 1 times 2 is 2, 1 times 3 is 3, filler 0. 4 times 2 is 8, 4 times 3 is 12. 2, 3 plus 8 is 11, carry the 1, 3, 1, and you count your decimal places, 1. So I've got 131.2 times 10 to the 17th power, which is not okay. I got to take this to the left to the left. That's another Beyonce problem. And make it 1.312. And if I go to the left, which means I'm dividing it, I have to increase this exponent by the same number of places. I went left 2 places, so this goes up. So remember, when I go left, that goes up. If I go right, that goes down. So the final answer for this is 1.312 times 10 to the 19th power. So even if you don't think it's 100% obvious, I think you will agree that this is much easier than addition. You don't have to do sneaky, crazy stuff to fix the exponents. Division. So say you had 4.2 times 10 to the 9th over 2 times 10 to the 6th. All right. If I had, say, for example, suppose I had 8 times 4 over 4 times 2. 8 times 4 is 32, 4 times 2 is 8, and 32 divided by 8 is 4. Let's say I decided to break these up into 2 separate fractions. 8 over 4 times 4 over 2. 8 over 4 is 2, obviously. 4 over 2 is 2, obviously. 2 times 2 is 4. Which you will notice is exactly the same thing we had. So that is basically the same thing I'm going to do over here. I do the mantisses, they do their thing. I do the exponents, they do their thing. 4.2 over 2 is obviously 2.1. 2 goes into 4.2. You could divide it out separately if you felt like doing it that way. You wouldn't have to. And 9 minus 3, or 9 minus 6 rather, is 3. Easy. Now, if this would have come out with the wrong number of digits, you would fix it just like we've been doing, and I'll show you what I mean by that. If you had 2 times 10 to the 8th over 4 times 10 to the 2nd, 2 over 4 is a half, which is 0.5. So that gives you 0.5 times 10 to the 6th, because 8 minus 2 is 6. The mantissa is not okay. You got to go to the right so that it's 5. And if you go to the right, this guy goes down 1. So that's your final answer. Got to watch that. Last possibility. Supposing you have something like 9 times 10 to the 5th over 3 times 10 to the 12th. 9 divided by 3 is 3. 5 minus 12 is negative 7. Because when you take a larger number from a smaller number, you subtract and take the sign of the larger absolute value. So this is actually a small decimal. And that's what happens. If you divide a number by something bigger than itself, what your answer is going to be a decimal. And a negative exponent just means a decimal. So I hope this has clarified how these problems work. I'm going to let it go at that. And I will talk to you later and hopefully see you live via Zoom soon.